Yes. It is visible.
Okay, then we will start with the SVM code. Here, all the libraries are imported, and you all have got the breast cancer dataset as a CSV file on Canvas. Please upload it from there. After uploading the dataset, copy the path of the file from here and paste it in under these brackets, under the codes. And then the data is shown here. And we can see the data. It is a breast cancer data set which has 32 columns, and the last column is 32 columns, and these two columns, diagnosis is the target column, which is malignant and benign classes, and the IDs column is useless according to features. So we will drop the ID column from the data, and again we have to convert into, according to SVM, we have to provide the classes as -1 and +1 for these two classes, malignant and benign. So we will take M index for data diagnosis. It will take the data diagnosis column and check if it is equal to it is equal to M class, and if it is equal to M class, data.loc command will take out the all rows which has M class, and dot index will provide the indices for that. Same for the B index, it will take out those rows indices which has the class B. Then the M index indices will provide the class equal to 1, and the benign indexes will provide the class -1. Then the data will transform in this file. There is no ID, and the diagnosis is transformed into -1 and +1. So you all are able to do this. You can try. Now we have to normalize the data. So using min-max scaler from the scalar library, we will normalize the data. And for this, we have to separate the data as well. So Y column will be take the target vector, which have diagnosis column. All rows of diagnosis column will take as Y in Y vector, and X will take all columns except the first column. The one is showing here. The axis takes all column entries except the first column, because first column is diagnosis column. So now our X data is the input data and label data is Y data. And to normalize the data set, we will provide the min-max scalar.fit transform on X data set values. And again, we will print the data frame as normalized data set. So I hope you all are able to do this. Now the further task is to split the dataset into train and test sets. So we will use the scalar library to train test split, and 4 groups are divided, and 20% data will be goes to the test data. And These are the printed results of samples of train data and test data. Now we will start the SVM. We will do the soft margin SVM here using Hinz loss. So first we have to define the loss function, the cost function of us. Random state. Uh, in this code or other code? Okay, random state equal to 42. Actually, we have to take the 80% data in the train group and 20% data in the test group. So the random state equal to 42 will ensure that the data will not biased. Like the data will not take it as the first 80% samples are goes to the train group and the last 20% sample will goes to the test group. That means the if first sample is taken in the train group, then the second sample will take after 42 samples to the train group. This will ensure the randomness into the data, and the similar features or similar samples will not goes into the train test data set. I hope you able to understand. Okay. So we are defining the cost function here. The weight matrix, we are defining, we have arguments as for weight matrix, X input data, Y label data, and C is the cost coefficient. So N is the number of samples, X dot shape 0 will provide the number of samples, number of rows in X data, and distances, which is 1 minus Y multiplied by X transpose W, which we have seen in SVM, defined in distances variable. So here in soft margin, we don't need the points where the margin is less than 1. Sorry, margin is greater than equal to 1, because these points are already classified. Whenever the distance is less than 0, this margin will be greater than equal to 1. That means these points are already well classified. So we don't need to classify them. We only classify the point samples which are misclassified. So the loss variable has the C multiplied by sum of the distances divided by N. You can remember the formula. C is multiplied by the sum of 1 minus Y X transpose W divided by number of samples. 4 multiplied by norm of W square plus this term. So this is the Hinz loss, and the 0, 0 is representing here that because W transpose W will be a one value only, but in a numpy array form. So to extract this value, we have to provide the 0, 0 index, and the definition of cost will return this cost. So here we have defined two main definitions to minimize the loss using gradient descent. So first we will define this definition, because this definition will use in this function definition. So to understand N, the number of samples, distance is as 1 minus Y X transpose W, and this is the negative distance where distance is less than 0. So negative distances are the indices of list of indices where the distance is less than 0. And we have initialized the gradient here by the W weight matrix will have the dimension of D cross 1, where D is the number of features. Here we have 30 number of features. So W will be 30 cross 1 vector, and dW will be the gradient of the function with respect to W. So we have initialized the matrix by the 0 matrix. It will also be a vector of 30 cross 1. So we have initialized here. Now we will run a loop for every component of W because it is a vector. So for every component of W, we have to compute the gradient. So the temp is a variable defined here, which is the gradient of this function, the loss. If we take out the derivative of this, we will got x multiplied by y multiplied by c, because this is the derivative with respect to W weight matrix. And again, the temp variable will be assigned by the gradient helper, and the temp variable assigned here will be goes as an argument here, and negative distances also. Now we will go for this function definition. So this is a gradient helper. What this will do is it will drain out the gradients of those points which has the distance negative. So which are the points which are already classified, it will not take the distance, it will not take the gradient of these. We have to not minimize the loss for these points. So for I again, the loop will go for negative distance is a it is a tuple of indices where the distance is 0. So let's assume the indices are 2, 5, and 7, where the distance is less than 0. So negative distance 0 will extend these indices. So I will go to for the first indices. First is 2. Then this is a variable defined. So it will take out the distance. It will take out the 0 is the 2 first index, and negative distance will take out the index of this negative distance array. It is an array of 2, 3, 7, and 0i will take out this 2 from this array, and we will provide the gradient of for this index is 0, and it will return again the gradient vector. Temp is a gradient vector which stores the gradient of all for all components of W. So now we have only the gradient for which points where which are misclassified. So here now that temp variable has only the gradients which are misclassified after calling this function. Now we will update the weight components of W. It has only one column. Let's try 0 here, and for every row for the W1, the gradient is, because we have the definition is here, 1 by 2 multiplied by W transpose W. The derivative of this will be W only, and minus of this gradient, and sum is already given in the definition, and also divide by n. This will return the gradient of for every component of weight vector. Then we will train the data using gradient descent. We will import the accuracy score from sklearn library and the shuffle command from sklearn library. Now we will define the cost coefficient here, which I have taken as 5,000. And we can initialize the weight matrix as 0. I already told that the W is a weight matrix of 30 cross 1. So the extend dot shape will be 30. And so it is a 0 matrix of 30 cross 1. And iteration will be taken up at 2000. You can take according to your requirement. And learning rate is this. So we will define an empty list of losses. So here for we have defined underscore here. This is because we don't need any indices of I. Earlier we have defined I, but in this loop we don't need I anywhere. So we can define underscore, like we don't care about the index of for loop. So we can define for loop this type also. So for underscore in the range of num iterations 2000 here. For every iteration, these all the things under the for loop will do. First, we will shuffle for every iteration the xtrain bytrain data. To not taking the same experiments, same results for every iteration. And now we will compute the loss by providing the arguments weight matrix, xtrain, ytrain, and the dot reshape function will ensure that the ytrain is a column vector of 455. 455 has been taken from here. Ytrain is 455 cross 1 vector. That's why. And C is the coefficient. You can again see the loss definition, cost definition here. We have 4 arguments: weight matrix, input data, label data, and cost coefficient. So we have provided these 4 arguments in this function. And in this empty list, we have append the loss for these parameters. For first iteration, the loss is appended in this list. So again, we have to compute the gradient, which is dw. The gradient definition we already have defined here. Gradient of with 4 arguments. So again, we have provided these 4 arguments and get the gradients of the weight matrix, gradients of the loss function with respect to weight matrix. And this is the formula of gradient descent. And then we want to print the loss, which is the cost. So for this iteration, after all the iteration, the loss will print up. After all iteration, the loss is this. And plt.plot losses will plot the losses for every iteration. The loss is minimizing. Now to testing the data on this SVM classifier, we have to, you are able to plot this. Please type these functions and commands in your cell and try to plot this loss plot in your cell. So I hope now we can go for the test data. So y predicted vector will be take the dot product of x test and the weight vector which is optimized, and np dot shine will ensure if this thing is greater than 0, then it will provide +1, and if the thing is less than 0, it will provide -1. So as we want the label, and y test will be an array which will reshape in 1141 because we have the test data as 114 samples. So we have to ensure that by predicted will contain the -1 and +1 value as integer, not as -1.0 and 1.0. It will make trouble in accuracy computing because we have to check 1 equal to 1. So we will convert these data into the integer form as we will take as type of integer, and from accuracy score command of sklearn library we will compute the accuracy which is here. So if you have any doubt in this SPM code, you can ask. After this, we will start the code for optimizer comparison on non-convex loss landscapes.
So there is some doubt in the chat box.
Sorry, I am not able to see this.
Random state, I think. What?
Random state is already answered, ma'am.
Okay, okay, okay.
Okay, so then now I will start with the comparison of optimizers, different optimizers on non-convex function. So here we will learn a new library which is Torch. So Torch is a deep learning library and which contains arrays as a tensor form and also contains automatic differentiation and differentiable functions. So it will ease to do differentiation task in deep learning with the help of this library. So and torch.optim will provide the optimizers, and as I say that the torch library will take the differentiable functions. So sin x and cos y will also define as torch.sin x and torch.cos y to take the computation of these. And this is our function sin x plus cos y plus 0.1 multiplied by x square plus y square. So we have to take initial point for every optimizer. We have to randomly initialize it. So it will take the point in torch. We will take every array or every point by the tensor in a tensor form. So we will provide the torch.tensor command here. And learning rate is defined here and steps, which are the iterations. So we will create a dictionary of optimizers. So we do not have to compute again and again every optimizer and do the same computation and that make the code large. So the optimizer config is a dictionary here which contains what is the please try to remember what is a dictionary. Dictionary contains items with the key value. So these are the key values here. SGD is a key value which contains the SGD optimizer. SGD momentum is a key value which contains the SGD momentum optimizer. And lambda is a function in the torch library which differs the creation of optimizers for every parameter P. P, what is the P? P is the coordinate on loss landscape. We have a landscape here. You can see. So we have to take the trajectory on this landscape. So we have to define P so that the optimizer path will be remain on this landscape. And so optim.sgd will create the SGD optimizer for this P and the learning rate. And again, these all optimizers will create it for learning rate and momentum. And we will create an empty list of trajectories. So now we will run the loop for each optimizer. Here, name is representing the string key value for this. For name, that means for name, optim function in optimizer dictionary will take the first item. Name will corresponding to the first item first. Then again the loop will run. The name will corresponding to the second item of this dictionary. So we are on, let's assume we are on the first iteration. So we are on SGD. And this command is a lambda function that takes a parameter tensor and return the corresponding optimizer of that. It will we will learn this at this point. It will take a point and return the optimizer value for this. These all functions are already defined, inbuiltly defined in torch library. So we will first initialize a point. We will first initialize the point, initial point already defined here as a tensor dot clone. So the dot clone command ensures each optimizer start from exactly the same point. So it as we go for the next optimizer, it will take the same point, not the point where the first optimizer has ended. And detach will ensure the previous computation will not go in the second optimizer computation. And dot requires gradients. True means we have to take gradients of the function for this point. because we are using all gradient based optimizer, so we require gradients. That's why we define true here. So here it will return the optimizer for this point. And now we will create a list of trajectory name, which will take the points in an array form. It will take the first point and detach it, and then in the numpy form, so that we can plot it in the plot, and dot copy will ensure the point will copy in this list. So here the optimizer will run for the iterations. Again, the underscore, because we don't need the index of for loop in the loop. So for in range of steps for 100 times. So this optimizer zero gradient will ensure to reset the gradients after each computation, because if we don't apply that, then the gradient will add up to the previous gradient. We have to take the fresh gradient for every point. So this command will ensure that. And loss will be taken for the point 0 will the x indices, and point 1 is the y index. So loss will computed. So fxy is our loss here, because fxy is our objective function which we have to minimize. So f is defined already. Then loss will computed for this, the point, initial point. Then the loss dot backward will ensure the back propagation to compute gradient of loss with respect to the point. And optimizer dot step will ensure that update point using the computed gradient according to the rule, the SGD rule. Step, we have to update step every time. So this will do that. Now each point will be added in this list dot by append command. And now trajectory is a dictionary. We have defined an empty dictionary. So we will take a key value of name and define and enter the points, array of points, which will again updated using SGD. The name is SGD here. So it will create a dictionary which has key value SGD, and SGD has an array of the points which are computed again and again by the update formula. Again, we will take the second optimizer here, SGD momentum. Then again the same thing has been done. Then it will add up by the key value SGD momentum, the array of points. So it will run for the 5 optimizer, the for loop, name, optimize function in optimizer items. Items will take the first element, second element from the dictionary. So when the loop is ended, we will plot the graph, because we have all things separately in a dictionary, every point array. So we will define x and y by creating a line space between -3 to 3. And then the mesh grid of xy And again define the function by using NP library, because to plot this function we have to use it. Z is the function, and we have to define the figure window here. The figure size will be 10:5. So it is a 3D figure. So we have to define a 3D axis as AX1. Projection 3D will add up a 3D axis in the figure window. So the AX1 dot plot surface will plot a surface plot of X, Y, and Z, and color map will be viridis here, and alpha is for transparency, if you remember, for the surface plot. And for name will be goes for SGD moment, and for every array in trajectories item for dictionary items. So first we will go for SGD. It will take the first item of the dictionary of trajectories, which is an array. So Z trajectory, the variable will define the Z values for these points, because till now we have only XY points which are minimizing Z. So we have to plot Z for this every point. So NP dot sign this trajectory colon 0 will ensure the X values, because the function is sin X, and colon 1 will take Y value of the array, and again this will take the X value and Y value here. So it will plot the X, Y, and Z on AX1 figure window. So these are the titles and labels for the figure and legends. Again, we to visualize well, because in this figure we can't visualize. We have to plot a contour plot. So AX2 will be another figure. So in contour we will define the dot contour command will plot a contour figure for X, Y, and Z, and label 50 will ensure that these lines, these are the curved lines. So these are curved for 50 times. And again the color map. So for name, it goes for optimizers. Array in trajectories items, it will plot the XY values. We want to show the path only, so it will take only XY values here. And the scatter will, the -10 means the last value of the array. That means the stopping point of every optimizer, the X point and the Y point, we have to show it by a scatter. That means a big point as equal to 40 for the size. You can see here the dot, the big dot is showing the last point. So these are the labels and title. The plot is showing here. For all optimizers, we have taken this point. Now we will learn what is the impact of the initial point for the landscape, because we have taken, so firstly this is the global minima of that function. So we have taken the initial point near the global minima, that's why it is going here. And these are this thing, and you can see if here these two are the local minimas, and this is a saddle point which is the curvy nature here. So here we have -1 and -1.5 point. So we will take, let's assume 2 and 1 point. So we will change this. I will run the code. 2.0 and minus 0.0.
Mr. Bharat Poddar, do you have any doubt? Mr. Bharat? Yes, Mr. Bharat, do you have any doubt?
No, ma'am. No.
Okay.
So if we change the point, it will goes to the near minimum. That's why we say the optimizers will stuck in the local minima, but you can see the SGD momentum is trying to escape the minima here, also here, and other optimizer like Adam RMOS top will may also can escape by changing the parameters of learning rate and initial point. You can try to define initial point again and again and check what is the trajectory of these optimizers. Then you can learn how optimizer behaves on these type of landscapes. The only one graph is not ensuring that the one optimizer is well behaved here. The parameters plays a big role in this. So if you have any doubt, and please try to change different points and different parameters of learning rate for each optimizer. Then you can see the impact of this thing. If you have any doubt in this code, you can ask. Here also we have taken only 100 steps. So you to escape the local minimas or to try to enhance our optimizers, you have to take more step like 1,000 or 2,000. It will take time. So you can see the results by changing these parameters, learning rate and step size. Steps. So now we will start with LDA code, the session of PC LDA from first day. You have learned the PC and LDA. PC code is already done. Now we will do LDA. So import all the libraries. Again, we will use the breast cancer dataset by sklearn library here. So data has been taken in the data variable, all the data of breast cancer, and DF will create a data frame by taking the data of in this variable and the feature names in columns, and the target column will be taken So we have to separate it in X and Y, the label vector and the data. So this command will take all the values except the last column. -1 is the last column. You can see the target is the last column. And this command will take the last column only. If we provide the colon, it will take the all values except the last column. And if we don't provide the colon, it will take only the last column. So X and Y are separated here. Now, if you remember, we have to define a between class matrix and a within class matrix in LDA. So first we have to define class means. For each class, the means of features. So for C in NP unique Y provide Y has two values, 0 and 1. So NP unique Y will take all the values as two values only, 0 and 1. It is an array of 0 and 1, but first the Y is a vector for many zeros and 1. So C for loop will run 2 times for C in Y, and class means is a empty list here. So class means will be appended by the dot append function. Class means will be added. For np dot mean command will conclude the mean of the data. This x y equal to c will take data rows only for which y is the label is equal to c. So let's assume the c is first for the 0. So it will take only the data for which the class is 0. So this condition is fulfilled, then it will take the mean across the rows. That's why we have taken x is equal to 0. That means let's take if this will take all rows that has the 0. So these are the 5 rows. So this will take all these rows and it will take the mean across rows. For this column across rows, the mean for this column, for this column, for this column, all. So the class mean will be added for every. So this will compute mean 30 times. We have 30 columns, and the class means list will be added by a 30 cross 1 array. This is an array of 30 entries here, and again the loop will run for the second class, which is 1. Then again the same thing will be done for the data where the label is equal to 1. It will compute the mean, and again it will add by the append command. So the class keys are shown here. This is for 0th class. This is for 1 class. These are the 30 entries. These are the 30 entries because we have 30 features. So overall mean, that means the mean of whole data across rows. So we have 30 entries for this too. For all features, this is the mean for whole data. Then we compute the between class matrix here. First, we have to initialize the matrix as a 0 matrix. So we have 30 features. H dot save 1 will provide 30 value, and the between class matrix will be a 30 cross 30 matrix, and np dot zeros will define a 0 matrix of 30 cross 30. This will initialize the between class matrix, and for C and mean vector of class 0, it will the zip command will zip the class means with y label vector. That means these are this whole array will be connected by the 0, and this whole array will be connected by 1. So for C and mean vector, so it will take the class and the mean vector. So 0 class and mean vector, the whole mean vector. This is the mean vector. So for we are on the 0 class first. So n is for data y equal to c, means where y is equal to 0, 0. For the data where y is equal to 0, the all data will be taken. So the all rows will be taken where the class is 0, and dot shape 0 will provide the number of sample where class is 0. So n is the number of samples where class is 0, and the mean vector will be reshaped by for the 30 cross 1 column vector here, and overall mean will also be reshaped by using dot reshape command. It is also 30 cross 1 vector. Now try to remember the formula of between class matrix, which is sum of c equal to 1 to the class up to the class, and multiply the samples of belongs to that class, the mean vector minus overall mean multiplied by mean vector minus overall mean transpose. So it will add up 2 times, because for 0 class and for 1 class. So SB is a between class matrix, which is a 30 cross 30 matrix. So SB0 will show the first row of this 30 cross 30 matrix. So it has 30 entries, obviously. Now we will compute the within class matrix. It is also a 30 cross 30 matrix. So we have to initialize as 0 matrix here. And for C in 0, NP unit will take 2 values only, 0 and 1. Class scatter will again define a 0 matrix of 30 cross 30. And X will take data from X, the for X is the index command. X will take the sample in the data where Y is equal to the 0 class. Because for within class matrix, we have to take the samples for each class. So X will go through the sample for in the data where Y is equal to 0, and all row will be taken for the sample, and again it is a 30 cross it is received for 30 cross 1 vector to maintain the computations, and mean vector will be taken as class mean C. That means the class mean of class mean vector of 0 class, and it will again be shaped by 30 cross 1 vector. Class means are here, so class mean of 0 class is taken it only. Now class scatter will be added up by X, the data point, sample minus mean vector multiplied by sample minus mean vector transpose. So if you remember the within class matrix formula, first is a summation for the classes, C equal to up to the classes, and the second for the samples for each class, and then the sample xi minus over mean vector, again xi minus mean vector transpose. So it will add up for all data points, and it will transfer the class scatter and add up in the zeros, because first is the between class matrix is 0. Then again this loop will continue for the 1 class. Then again the things will done, and it will add up in the entries of within class matrix. So it is also a 30 cross 30 class matrix. So first entry will have 30 entries, first row. Now we have to compute the eigenvalue and eigenvectors. For this, we can use NumPy library. This command, eigenvector and eigenvalue computed for the within class matrix inverse and multiplied by between class matrix. We have to maximize the between class matrix and minimize the within class matrix. That's why we have taken, according to mathematical formula, if you remember the session, as W inverse and SB will be multiplied for that, and the eigenvalue, eigenvector will be projected the data for the components of features. Now, we have two short eigenvectors and eigenvalues. Again, we have to, the argsort command, argsort command will arrange the eigenvalues in an ascending order, and this command will reverse the order. So the first eigenvalue will be the greatest eigenvalue, and eigenvectors again rearrange according to the eigenvalues. IDX is the indices of the eigenvalue, so it will rearrange, and we will take only two components here. So that's why we have taken only two eigenvectors, first two eigenvectors of the first two greatest eigenvalues. So we have to project the data in these two components. So XLDA variable will take X transpose W, and this is the array of XLDA. So we the original data shape has 30 features, but after LDA, we have only two components for all the features. We have taken only two components, so the now data features has reduced. So the modified data shape has only two features. Now we can visualize the data points for these two features and visualize the classification. So tlt.scatter command will plot all the data points. For the first component, XLDA has two vectors. So it will take the first, it will take the second column. It will take the first column, it will take the second component data points. And C equal to Y, the class separation, the color will be different for the Y has two values 0 and 1. So it will automatically take different colors for 0 class and 1 class. And again the labels and title. So you can see now we have only two features, and almost the data set can be visualized and can be classified very easily now. So this is the use of LDA. The data is now linearly separable by a line here. So now the LDA code is complete. If you have any doubt in this, you can ask. try to write these commands on your cells